Well, hello 403ers. This is my third makeup video, second take. I am now going to be dealing with our next circuit. We just did a differentiating slash high pass filter. Now we want to take a look switching the resistor and capacitor of those two. So I've got my voltage in. This is some potentially time varying signal. Now I want to put, instead of having a capacitor here, I'm going to put a resistor here. I want to put my capacitor up top. So I've got capacitor C, resistor R. So from the high pass filter, all I've done is I've flipped them. Now if you think what's going on here, right, my signal, my DC values can come in perfectly fine and hit this negative. My high frequencies cannot come back to get amplified though. Or I should say actually my high passes, low frequencies can't come back. The high ones can come back and they get sent, this is at ground, so it gets killed off. So in essence, the high frequency ones are going to get damped out on this negative feedback. The low frequencies are not. So low frequencies will be amplified, high frequencies will be killed off. That makes this a low pass filter. So this is low pass. And this is akin to what you would see in a simple first order low pass filter that goes on. Right, V in to V out. And you could also use this circuit, but it's not as ideal as this one is, because this one will nicely stabilize. Again, the op amp has really high impedance and all kinds of nice properties like that, which this one does not have. You put a load on here, you can drag this down. You're not dragging this down. So, you know, nice properties here. We're going to stick with this one. This is a first order. This is first order. So in that sense, the low pass works out good there. I guess I should actually use quotes there. Okay. So we want to go and analyze this and figure out that this is an integrator. When we take a look at our node law, again, this is V minus, this is our V out. So node laws tells me this time we go here, we get V minus the V over R. That's the current flow here. Now we're going to get the current through here, and again we remember that this is going to be plus, I get a C times the voltage difference, but it'll have to be derivative, so I'll take d dt of the voltage difference, which is V minus minus V out. And that has to be equal to the current that's flowing in there. For an ideal op amp, that's 0. Alright, that's wonderful, and we say great. We can now note the fact that V minus has to be equal to V plus, and V plus is ground. So therefore, you know, these terms right here will go away. I got a minus on both of these, so I can just distribute through, and I end up with the simplified formula that my input voltage V over R plus C times d dt of the output has to equal 0. Alright, so you just say, hey look, it just has the derivative again, but I've got the derivative of the output, and I just want to know what the actual output itself is. So if I rearrange some terms here, I end up with the equation that this has to be d dt of my output has to equal to minus 1 over RC. There's my time constant and the inverting because it's on the negative input. And this is times V. And I left some space here because what I'm going to do now is integrate both sides with respect to time. When I do that, this goes away. I get V out. But now I have the integral of V over here. So I have an integrating circuit, which is a low pass circuit. And just like I talked about in the last video, if you think about this in terms of that whole thing with sine and cosine, If I take a look at integrating cosine of omega t, I end up with respect to time, I end up with 1 over omega times my sine omega t. And so you'll see that for low frequencies, as this gets small, the amplitude gets really big. So low frequencies go through fine. As I go to high frequencies, the omega goes to infinity, 1 over omega goes to 0, so high frequencies get killed. So integration has to be a low-pass filter. And that's what this does. So yippee skippy, you now have another circuit to add in, integrators if you want to treat it mathematically, or a low-pass filter if you want to treat it signal processing style. So there we go, that takes care of that, and I'll move on and get your next video here in a few secs. Hope this makes sense. Take a look over the book. They give you some examples, and we'll do this as a lab on Thursday. Talk to you soon.